In this video, we're going to be discussing directing groups on benzene. When we react phenol with bromine, we get this product. But when we react nitrobenzene with bromine, we get this product. Why is there a difference in the positions of these bromines? To explain this, we need to look at phenol in a bit more detail. So in my previous video, I explained how phenol increases the electron density in the ring through the donation of the oxygen lone pair. But this oxygen lone pair doesn't distribute the electrons evenly. It targets specific carbons with that electron density. So it targets the 2, 4, and 6 positions on phenol. To explain why it's these carbons that have the higher electron density, we need to look at something called resonance forms. This next part you don't need to know for A-level, but I think it's very interesting and will hopefully give you a better understanding of directing groups. At A-level, you usually see benzene rings drawn like this, and you're discouraged from drawing them like this because, as we know, Kekulé's model of alternating double and single bonds isn't correct. But sometimes it can be helpful to draw the benzene ring like this, as long as we know that these double and single bonds aren't really double and single bonds, and they're somewhere in between. So these bonds can move around the ring and go into the alternate positions like this. So what I've drawn here is actually an example of a resonance form, where each drawing doesn't tell the whole story, but together they provide a more accurate picture of what's going on. So now let's look at the resonance forms of phenol. So the oxygen lone pair can come down and form a double bond between the oxygen and the carbon. But because carbon can only form 4 bonds, this carbon has to break one of its bonds. And that bond is this one. So the double bond breaks and the electrons from that double bond go onto this carbon. So if we draw out the result of this, we'd have a double bond between the oxygen and the carbon. This oxygen is going to have a positive charge because it's donated electrons away from itself, and it has 3 bonds. These bonds are going to be unchanged, and we're no longer going to have a double bond here, and instead we're going to have a negative charge on this carbon because it's gained the electrons from that double bond. And we can move this negative charge around the ring, so the electrons from that negative charge are going to form a new double bond in this position, which forces this bond to break, because as before, carbon can only have 4 bonds. So then we get this. With a negative charge on this carbon. And once again, the charge can hop around. So we get this. So with the charge there, and then we can get back to almost what we started with, but just with the double bonds in the alternate positions by doing this. So we're forming a new double bond here and breaking the carbon-oxygen bond, and that takes us to this structure. Okay, so hopefully you can see from this that there are specific places where this negative charge is localized, and we can draw an overall picture of what all of these resonance forms look like put together. So we're going to have dotted lines representing the partial double bonds, or the delocalized system, and a dotted line down there. This is going to have a partial positive charge, and then we've got these partial negative charges at these positions on the ring. So there is no way that we can get the negative charge on the 3 and 5 positions. So it's the 2, 4 and 6 positions that have the greatest electron density, and these are the positions that are going to be most attractive towards electrophiles. So let's summarise this. Phenol is an example of an electron donating group because it has that lone pair of electrons. It is an activating group because it makes the ring more reactive towards electrophiles, and it directs towards the 2, 4 and 6 positions. So our OH group was one example with the lone pair. Then we have an NH2 group, which also has a lone pair that can donate into the ring. And we have alkyl groups, like methyl groups, ethyl groups. And although these don't have a lone pair, they can still push electron density into the ring. Now we know that phenol directs towards the 2, 4 and 6 positions. It's time to understand what's going on with nitrobenzene. So why does it direct to the 3 position? Like with phenol, we can draw resonance forms for nitrobenzene. So this is what nitrobenzene looks like when you draw out the full nitro group. And this time we have an NO double bond, which can withdraw electron density out of the ring. So to show how this works, we have electrons from this double bond moving to this position to form a double bond between the carbon and the nitrogen, and then the electrons from the double bond move up onto the oxygen. So this results in a double bond here and a single bond with a negative charge. We've still got the single bond negative charge up here, and the nitrogen is still going to have a positive charge because it still has these 4 bonds. And importantly, we have a positive charge on this carbon because the electrons from that double bond have moved away from it. And as before, we can move this charge around the ring. So I can draw this moving to that position, that puts the positive charge on this carbon, and again the double bond can move to there. Putting the positive charge on this carbon, and then if we wanted to, we could reform the structure that we had up here just with the double bonds in the ring in the alternate positions. So the electron pair is going to come down, this bond is going to break and move to there. Okay, so again we can draw an overall picture of what's going on. So I'm going to draw dotted lines to represent the delocalized parts of this structure. Dotted line there, and we're also going to have dotted lines across here. We're going to have partial negative charges on these oxygens, and then partial positives on these carbons. So the positive charges have gone on to the 2, 4 and 6 positions, which leaves the 3 and 5 positions with greater electron density than the 2, 4 and 6. So what this means is that these carbons are the ones that electrophiles are most attracted towards. So let's summarise what we've just discussed for electron withdrawing groups. So these are deactivating because they pull electron density out of the ring and make it less reactive towards electrophiles. And they also direct towards the 3 and 5 positions. So some examples of these are the nitro group, which we just looked at. We could also have a carbonyl, so maybe an aldehyde or a ketone or a carboxylic acid. Basically any structure that has this CO double bond or an NO double bond can withdraw electron density out of the ring. And the final example of one of these would be a CN triple bond, which can also withdraw electron density in a similar way. So this bond can break and the electrons can go up onto the nitrogen, just like it can in all of these examples too. Now the exceptions to what we've discussed so far are the halogens. So these are fluorine, chlorine, bromine, etc. So if we look at fluorine, so fluorine is a very electronegative element, so it's going to withdraw electron density out of the ring by an inductive effect through the sigma bonds. So this deactivates the ring, makes it less reactive towards electrophiles. However, fluorine also has a lone pair, so it can, to some extent, donate electrons back into the ring using this lone pair. And as we saw before, this puts electron density at the 2, 4 and 6 positions. So overall, the fluorine is withdrawing electron density out of the ring, but then it's just putting some electron density back at the 2, 4 and 6 positions using its lone pair. So in summary, it is an electron withdrawing group it's deactivating, which is what we would expect for an electron withdrawing group, but then it directs to the 2, 4 and 6 positions, which is not what we'd expect a normal electron withdrawing group to do. So let's look at an example. So let's say we start off with our benzene ring and we want to add a methyl group and a nitro group to this ring. So we could either add the methyl group first, like this, or we could add the nitro group. And then we just have to add the other substituent to the ring, so in this case the NO2 group. But the question is, where on the ring does the NO2 group add? So we know that CH3 is an electron donating group. It's activating and it directs towards the 2, 4 and 6 positions. So we'd expect our product to either be this with the NO2 group at the 2 position, or this with the NO2 group at the 4 position. So the 6 position product is just going to be exactly the same as the 2 position product. Over on this side, we want to add our CH3 group, so where's that going to go? Well, NO2 is an electron withdrawing group, it's deactivating, and it directs towards the 3 and 5 positions. So this means our major product is going to be with the CH3 group in the 3 position, because the 5 position would just be exactly the same as this product. So you can see that because of the effects of directing groups, we can get different products depending on what order we do a series of reactions in. If you found this video helpful, please like and subscribe. I've made previous videos on the structure of benzene, its mechanisms, and a comparison to phenol, So if you want to check those out, there'll be links in the description.